Alright, welcome back. This is part 3 of our lecture about paleoclimate and what paleoclimate is telling us about climate change. Now, I've been talking about different methods, in particular with like ice and so on, but also corals and so on, that are ways of using the chemistry, which is sort of a bit of jargon to mean like the ratios of different isotopes in the material, to infer something about global mean temperature. It's time to actually dive in and figure out what that means. We're going to use water as our example of a way to use chemistry as a way of about figuring out global mean temperature. This can actually be done with different materials and so on, but let's look at a water molecule, okay? This is just a regular old molecule of H2O, 2 hydrogens, 1 oxygen sitting right there. But the oxygen atom that's in every water molecule, well, it has the potential to be different. It has a potential to exist in 2 different isotopes. Now, if isotope is a word you've forgotten from a long time ago chemistry class or something like that, let's just be clear here. An isotope is each of 2 or more forms of the same element that contain equal numbers of protons but different numbers of neutrons in their nuclei, and hence differ in relative atomic mass but not in their chemical properties. In particular, it's often a radioactive form of the element, although in the particular case we're looking at now, it's not generally a radioactive thing. As it happens, under the conditions we see on Earth, we have water molecules that contain one of 2 different isotopes of oxygen. There is so-called oxygen-16, and oxygen-16 contains 8 protons and 8 neutrons. It's the adding up of the protons and the neutrons that gives you the number 16. And that is a common form of oxygen, but there is a non-negligible amount of oxygen in the Earth system that is oxygen-18, where it is still 8 protons, but now it is 10 neutrons instead of 8 neutrons. And that is also a more or less stable form of the oxygen element. And because they both have 8 protons, chemically they're the same. They bond with hydrogen molecule atoms to make water molecules in exactly the same way, but they are slightly different. They have slightly different masses. So we get some water molecules out there that contain an oxygen-16 atom, and there are some water molecules out there that have an oxygen-18 atom. There are therefore some water molecules that are slightly heavier due to the differences between the 2 different isotopes of oxygen atoms that are out there. This is not the same thing, by the way, if you've heard this term heavy water. Heavy water is a different story, but in fairness, these water molecules do have slightly different masses. Now, when you drink a glass of water or whatever, you are drinking a mixture of water that contains oxygen-16 and water that contains oxygen-18. Now, in general, those materials exist, those 2 different isotopes of oxygen exist in known ratios in the world's oceans or wherever you want to see. On Earth, there is a certain known mixture of oxygen-16 and oxygen-18. But it turns out there are some physical differences between water that is based on an oxygen-16 and water that is based on an oxygen-18. In particular, they do have different evaporation rates, and their evaporation rates are differently functions of temperature. They respond differently to temperature. At relatively low temperature, as it happens, the heavier molecules of water based on oxygen-18 evaporate at a slower rate than the oxygen-16 based water molecules. So in the atmosphere, the humidity that's in the Earth's atmosphere will be an anomalously large amount of oxygen-16 based water vapor molecules compared to the amount that would be, like, say, in the world's ocean. The ocean, when the water temperatures are cold, the ocean is relatively enriched in oxygen-18 water molecules, and the atmosphere is relatively enriched in water vapor that contains oxygen-16. Okay? Well, that water vapor that's in the atmosphere with all that oxygen-16, the residence time is very small. That's going to quickly fall out in the form of precipitation and so on, which returns back to the ocean in the form of runoff, except for, of course, the stuff that's stuck in ice. The precipitation that falls as snow may become trapped in a glacier, and now you have a layer of the glacier that is enriched in oxygen-16 and depleted in oxygen-18. And in the same way, if the world's oceans are a little bit warmer than usual, you get more evaporation of water vapor molecules that are of an oxygen-18 atom in it, and as a consequence, there's relatively large amounts of water vapor in the atmosphere that contain oxygen-18. that deposits in the form of precipitation and runs back to the ocean, except for the precipitation that falls on glaciers and becomes trapped in the ice. So you'll get a layer of ice that is relatively rich in oxygen 18. So see how we can actually go and get the ratio of oxygen 16 to oxygen 18 atoms in a piece of ice, and that tells you something about the temperature of the water that evaporated off of, say, the oceans and then became the precipitation that fell on the glacier. Now, of course, you have to make some guess as to where this water came from, but in general, water becomes pretty well mixed through the Earth's atmosphere. A good thing to say is it's just the global mean sea surface temperature or the global mean ocean temperature or whatever that is affecting this ratio of oxygen 16 to oxygen 18 in the atmosphere and ultimately in the ice. So everybody knows molecules deposited in the form of precipitation, and in the ice core we can take those molecules, those ratios, and we can determine the mean temperature of the surface of the ocean when that precipitation fell. For that matter, though, those oxygen atoms end up all kinds of places. I mean, we can remember like the ocean sediments. We can dig up the skeletons of microorganisms and so on that are in the ocean, and we can look at the oxygen that is incorporated into their shells and so on. It's also going to be oxygen atoms that came from the water around those creatures, so we learn something about the temperature of the oceans. Similar processes can be used about like the minerals in coral and so on. This is all nice ways to get real climate information from a natural paleoproxy like ice cores. There are other paleoproxies we could be talking about, though, and the one that the public tends to know the most about is tree rings. You know that the study of tree rings has the very cool name of dendrochronology. Okay, dendro as in branching, chronology as in building a timeline or whatever. And of course, you know where we're going with this here, right? I mean, if you cut through a tree or drill a core through a tree or whatever, extract a core from the tree, you're going to see that the tree's trunk is made of rings, and every ring represents 1 year of growth of the tree. And, well, for a living tree, it's pretty easy to establish what each of those rings, when they were grown. Because the outermost ring represents the current year, and farther back you get into time, you go closer and closer to the center of the tree trunk. So dating the tree is not so hard in that case. Now, in the case of if we want to extend farther and farther back in time to use the tree for paleoclimate information, well, there are trees that are extremely old, okay? There are trees that are thousands of years old on Earth, although in general we don't like to extract cores from them and take a very old tree and make it old and dead, although it doesn't always kill the tree, but that's a whole complication. It's actually another strategy is for dendrochronologists to actually go out and find old wood and look for overlap between those rings and the rings of living trees. See, for example, like this is the roof of a church in Ireland that was built something like 1,000 years ago. We have a pretty good date as to when these timbers were cut. I mean, because it wasn't like we cut down trees and then let them sit around for 500 years before we make them into boards. So these boards that are in this roof here, we have a pretty good idea when the oldest ones were made. And so if we can find a tree that's, say, 1,500 years old, and then see, oh, look, it had some wide ring, some narrow ring, some wide ring, and we find that same pattern in some old cut down tree, then we can match that up and say, oh, look, we can then extend back using this tree that was cut down 1,500 years ago and overlap that and now extend this climate record farther back into the past. Now, I think it's in general understood by it's kind of one of those popular science sort of things that the width of the rings of the trees tells you something about the growing conditions under which the tree experienced in that given year. And that can be that can be a number of different things, but that determines how wide the width is. But in any particular environment, it's typically the case that the growth of a particular species of tree is limited by one or more relatively small number, though, of factors. Often it's just the temperature, or it's often just the moisture. Either there's plenty of moisture there and what limits the growth is the temperature, or it's plenty warm, what limits the growth is the precipitation. Obviously there can be other reasons like fire and pests and so on, but by and large it's going to be limited by either temperature or precipitation, and people who study trees can tell you the answer to that. And so you pretty quickly have a proxy here. The width of these tree rings is actually giving us climate information about the temperature in that area. Or for a different species, it might be giving you climate information about the precipitation that was experienced in that area. And now you have a paleoproxy that can be extended back into the past. Dendrochronologists are also really fascinated by fossilized wood. Now, fossilized wood and fossil tree rings generally can't be pinpointed to a particular year the way a living trees can easily be done, and fairly, recent in the last 1,000, 2,000 years trees can be dated. But at least it gives you a sense of like the range of conditions that this fossil tree experienced. If this tree is living in an environment where it's very stressed for long periods of time and has lots of these very narrow rings, that tells you something important about the climate conditions when this long dead tree lived. Okay, so I mean, it can tell you can't pinpoint it to necessarily a particular year, but that isn't necessarily what the paleoclimatologist is looking for anyway. Let's answer a couple quick questions about this kind of more physical stuff about paleoclimate before we move on. Question 6. If the ratio of oxygen 18 to oxygen 16 is higher than normal in a layer of glacial ice, blank. A, the snow fell on the surface of the glacier in a particularly warm winter. B, the snow fell on the surface of the glacier during a particularly cold winter. C, the source of the water that fell as snow was unusually warm. Or D, the source of the water that fell as snow was unusually cold. Now that's kind of a tricky one. You got to know what it means to have higher values than normal values of oxygen 18, and you got to know about what that actually means. Make a choice from those 4 options and get a little feedback before you move on to question 7.